All right, hello everyone. Good afternoon. Happy Friday. So let's go over the exam that you have on Monday. Today is 3/5, March the 5th, 2021. So I'll go over the multiple choice part, important themes for Monday. So that's part of your test 2. So in case if you have any issues or problems, just email me, or if you have my cell number, it's on the syllabus, it's on my front door. You can text me. There's also a written portion. It should be open. Did you get a chance to print this out? Everyone have access to it? This is what you should have. It should be open and should be available on Canvas. If it's not available on Canvas for you to print out, please let me know, and I'll figure something out, but I believe it should be out. This is also due on Monday, so make sure you upload this. To Canvas, and that's the written portion of your exam. You want to show your problems and show your work here for full credit. Right, so the multiple choice portion of the exam is on Monday. We also have quiz 2 that's also due on Monday. So the way my system works, these quizzes that you see on Canvas, they're due the same day as the exam. Right, so one thing I do want to tell you guys is to bring your rate law sheet. You can use this for the test. Right, so there'll be some equations that you will need to use, okay, depending on whether the reaction is 0, first, or second order. Here we're talking about reaction rate. So make sure you bring this to the exam. Right? Have this by your side near your computer or when you're doing the written portion of the test. So use the rate law sheet. And the test is covering chapters 13 and 14. Okay, this is rate laws. And chapter 14 was equilibrium. Chapter 13 was rate laws and lowercase k. Chapter 14 was equilibrium and capital K. So let's go over the multiple choice, bless you, really quickly. Just a definition question for you guys. What do you guys think a catalyst will do? It will speed up a reaction, which means it's going to increase rate constant. The rate constant is, miles per hour, but in terms of a reaction. But in terms of equilibrium constant, K, it's going to be unaffected. Right? The equilibrium constant stays the same. Another thing a catalyst will do is lower the activation energy of a reaction. It lowers the activation energy of a reaction by 2 ways. Number one, it some way, somehow, through some mechanism, it increases the collision frequency. So you have the right collision frequency, and you also have the right orientation. Okay, so molecules have to hit one another to obtain their transition state. So they have to have the right collisions. Okay, it's not like it's got to be like this. All right, the right collision frequency and orientation. The molecules have the right or correct orientation and frequency, they can have the reaction go to products. We call this right at that moment the transition state, usually with a star by it. Catalysts help achieve the transition state faster at a lower activation energy. Remember, the activation energy, if we were to describe it, it's an energetic hump. It's kind of like a barrier the molecules must overcome in order for the reaction to go to the destination, in this case, the products. All right, so review your material on catalysts. Chapter 13 was all about rate laws, so we have a generic reaction, A plus B goes into C plus D. Usually the rate law is going to be rate is equal to your rate constant K times the initial concentration of A raised to some power. Raised to some power. And times the initial concentration of B raised to some power. So we can call it exponent B here, exponent A. So A and B is something you have to find. So you need a data table. It's just something you need to calculate on your own by doing the actual experiment in the lab. So A is going to decay, so we ascertain how fast the reaction is going to go. We acquire how fast a reaction is going to go based on decay. The decay of A and B will tell us how fast this generic reaction is going. So A can decay with first order kinetics. A can decay with zero order kinetics, first order kinetics, or second order kinetics. So all of those associated equations, all of the associated graphs for zero, first, and second order are shown here. Same thing with B. B can decay with zero order kinetics, first order kinetics, and second order kinetics. And the overall order of the reaction is going to be A plus B. A plus B. So let's say as an example, we do our equations and we do our calculations. We have an order of 1. So A decays with first order kinetics and B decays with first order kinetics. So that will give us rate is equal to rate constant K times the concentration of A times the concentration of B. So, one thing here is units. The units of this rate constant are going to vary. So the question I have here is what would be the units of K, rate constant, if A decays with first order kinetics and B also decays with first order kinetics? What will be the units of your rate constant K? Remember, the units of the rate constant K will vary. You see that here in your little cheat sheet, The units of K for zero order is this. Units for first order are that. Units for a second order are this. So the units of this lowercase k are going to vary. So what will they be for this reaction? So here's how you solve that problem. Rate is miles per hour. How fast we go. So usually we don't say miles per hour. We say molarity per second. So the SI unit, the base unit of time, is second. That's going to equal to K. The units of this bracket. This is the symbol for concentration, Very good, and that's M. So we're just talking units here now, not any numbers. We're just talking units. So concentration for this guy has units of M. The concentration for B also has units of M. So M times M is M squared. We're talking about units of K. That's what we're trying to solve for here. So we will isolate K in terms of units, and we will get M over seconds, and then I'll move the M squared to the other side. So my units of K for this reaction is going to be this is not right. It's going to be one of these M's cancels with one of these M's. So my units are going to be 1 over M seconds. So units of K is an answer, is a question on the exam. 1 over M seconds. What would be the overall order of this reaction if you say A is 1 and B is 1? What's the overall order? It'll be 1 plus 1, which is 2. The units of this K is something you'll have to solve, which is here. Okay. So basically there's a question on units in this exam. And by the way, big M is really just moles over liter. It's a concentration term. All right, moving on, and for the sake of time, let's say we have a reaction here. Let's say we have a reaction. Let me write for you a hypothetical reaction. CH4 plus 2H2S goes to CS2 gas plus 4H2 gas. Okay, first of all, you always want to check your arrows. So the back and forth arrow tells you that this is in an equilibrium. So always check your arrows in the reaction. This means it's an equilibrium, which means it will settle. Okay, so it will not go to 100% products. Okay, it will not just stay with 100% reactants. Okay, it's going to settle. Okay, either it will settle more here, more there. Okay, if it settles equal, 50-50, we call that an equilibrium constant of 1. So one side is not favored over the other side. So in essence, in an equilibrium, the reaction does not go to 100% completion. So it's going to settle. Right? Which way does it settle? Okay. First of all, let me give you some hypothetical terms here. Okay. Let's tell you the K for this reaction is 0.036. K. That has to be given to you, obviously. And K is always quoted at a specific temperature. So we'll say this temperature is 25 degrees C. Okay. K, capital K, is always at a specific temperature. All right, so let me give you some numbers here. Let's say we have 1 mole of CH4, 1 mole of CS2, 2 moles of H2S, 2 moles of H2. Okay, we have this in 250 ml beaker or flask. Okay. So the question is, are we at equilibrium? And if not, where will the reaction shift to get to equilibrium? So if not, where will the reaction go to establish equilibrium? So if, are these equilibrium concentrations? First of all, are these concentrations? No, we have to calculate the concentrations. So this is a common error. You can't just put moles into our equilibrium expression. All right, looking above, molar is moles over a liter. Okay, you don't put moles, but you have to put moles over a liter. Okay, what do you have to put it in? You have to put it in K. So K here, these are concentrations, moles over a liter. So it's going to be products over reactants. Okay, what do I have to do with that H2? What power do I have to put it in? 4th divided by reactants, products over reactants. All right, what do I have to do with that H2S? What product do I have to put it in? Square. Okay. So this is called the law of mass action. We know this has to equal 0.036. Okay, that's given to us in the problem. So a lot of students make this mistake. They put 1 mole here. They'll put 2 moles for H. They'll put 1 mole for CH4. They'll put 1 mole for CS2. Okay, that's not the right answer. Okay, these are concentrations, and concentrations, as you know, is in moles per liter. Right, so the concentration of CS2 is 1 mole over not 250 milliliters, but 0.250 liters. Okay, we have to convert that to liters. So this gives us 4m. The concentration of CH4, again, it's not 1 mole that goes in here. It's moles over liter, so it's going to be 1 mole over 2.250 liters. Okay, that's also 4 molar. Uh, 2 moles of H2S. Okay, we can't put 2 moles into our H2S. It has to be mole. Okay, we can't just put 2 moles of H2S in our equilibrium expression. What goes in here is moles over liter. So the concentration of H2S is 2 moles. Again, convert that to liters is 0.250 liters. That is 8 big M moles over liter. And then finally, the concentration of H2. Okay, we cannot put 2 moles into our equilibrium expression. Okay, we have to do it moles per liter. So that's going to be 2 moles divided by 0.250 liters. Again, in our calculator, we get 8 molar. Okay, now we can plug that in. Okay, now we can plug this in. Okay, I see a lot of students just plug in 1 mole in here, 2 moles in here, and that's not right. It's moles over liter that goes in there. Right. We plug this in, so let's plug that in here. So plugging this into our equilibrium expression. Okay, so CS2 is 4. H2 is 8, so 8 to the power of 4, so that's got to be 8 to the power of 4. Divided by CH4, the concentration of CH4 is 4. And the concentration of H2S is 8. Okay, so that has to be 8 squared. So that has to equal K, right? Doesn't that have to equal K? They give you the problem. I tell you that K is equal to 0.036. All right, so let's do this. The 4 and the 4 cancels. Okay, the 8 squared cancels with one of these 8 squares, leaving me with another 8 square. So something is very wrong here. 0.036 does not equal to 64. Okay, something is very, very wrong. So, well, how do we make this right? All right, are we at equilibrium, first and foremost? Yes or no? No. Okay, 64 does not equal to 0.036, which was the value constant given to you at the temperature. Okay, so we're not at equilibrium. Okay, so how do we write this ship to get it to equilibrium? Okay, which way will the reaction go to establish equilibrium? So here we can do something called the Gator Rule. So what I taught you was the Gator Rule. Your textbook has something else, but here we want to put Q first. Okay, Q, and then you want to compare it to K. So K, they gave it to you, or I gave it to you in the problem, is 0.036. Q is something we calculated. We know we're not in equilibrium because this inequality is there. And now you want to compare the numbers. And we will see 64 is much, much, much greater then 0.036, the equilibrium constant. So which way do the Gator jaws point? To the left. So which way will this reaction shift to get to equilibrium? To the left. Okay. So it will shift left. So if you're not at equilibrium, obviously these concentrations are not at equilibrium, but to get to equilibrium, it will shift to the left to establish this 0.036 number. All right. So this is called the Gator Rule, or Q. Q is called also the reaction quotient. Say hypothetically Q is equal to K when you do your problem. If Q is equal to K, if Q does equal 0.036, then all these concentrations are indeed at equilibrium. But they're not equal to 0.036, so we're not at equilibrium. And that's okay. It will go to equilibrium by shifting to the left, because that's where the alligator jaws point to. Okay? All right, so a problem like that on the exam. Multiple choice part. All right, let's move on to our next bullet point here. Okay, you got to remember here K versus lowercase k. What are the units of the equilibrium constant? K. There's none, right? So there are no units. Unitless, right? Unitless, very good. Do solids and liquids go in here? Okay, absolutely not. Okay, so this is very fundamental. No solids and no liquids. Okay, here we're looking to, which way will the reaction? Is it favored towards the products or is it favored towards the reactants? Okay, usually the reaction settles, some part reactant, some part product. We designate that with a back and forth arrow. Okay, K is a totally different ballgame. What are the units for K? Rate constant? It depends, right? It depends if your decay of each reactant is zero order, first order, or second order. Really can't answer this question. We need to, do some maths. Okay, here we solve. You'll have this problem on the test. You have to solve for the units of K. Okay, you'll have a type of problem on the exam. And remember, rate here in our rate law is not miles per hour, which is how you got here to Methodist, but it's molarity over seconds. Okay, how fast the reactants are decaying over time. All right, so here we have very units. Okay, so just keep that in the back of your mind when you're I've seen this in my previous years here. People confuse the two, and also I've seen people put solids and liquids in the equilibrium constant, which is not something you want to do. All right, let's go to our another bullet point here, bullet point 6. Okay, let's say I have a rock. Okay. A rock. Let me draw a rock here. Okay. And I have a rock that has a half-life of 12 years. Okay. So it's a half-life of 12 years, which means after 12 years, how much of that rock will remain? Half of it, which is 50%. Half of it, which is 50%. And, how does it decay? Okay, it decays with a half-life of 12 years, but how? Okay, how? Is it zero order, first order, or second order decay? You see, that's also important. I will tell you in the problem that it's first order decay, just for kicks. Okay, let's say you have first order decay, and all right, and I start off with this rock. Let's say I have, I don't know. Let's say I have 257 it's a very small rock. Okay, it's a itty teeny tiny rock. let's say I have 257 ppm. That ppm stands for parts per million. Really don't need to know this to solve this problem, but ppm is parts per million. It's a unit. Like your water, so much parts per million in your tap water. That's deemed safe to drink. Okay. So I have 257 ppm of this rock, and I want to know the time it takes to get to maybe 15 parts per million. Okay. Everyone see this problem that I've constructed here? All right, I got a rock, a piece of material that's half-life is first order decay. It's important that you know that it's first order, otherwise you can't solve this problem. If it's 0 or second order, it's a different set of equations. And I want to know the time that I have 257 parts per million of the rock, the time it takes for it to disintegrate, to decay. Remember the big word here is decay. To decay to this concentration of 15 parts per million. All right. So, immediately when I told you it's first order decay, okay, without hesitation, you should run and consult these equations for first order decay. Okay. And this problem, the way I told you, the setup, the half-life is 12 years, right? So we got a half-life of 12 years. Let's go ahead and solve for the rate constant k, lowercase k here. So it's going to be rate constant k is going to be 0.693 divided by the half-life. So we're going to use this right here. Solve for k. Okay, the half-life. The half-life, they tell us, is 12 years. Right, so so 0.693 divided by 12 is going to be 0.0578. Okay, 0.0577. I'll just put all the digits in. 0.05775 inverse years. Okay, inverse years meaning I'll put the years to the power of -1. So this is our k. All right, that's good. That doesn't really solve the question here, which is the time. Now we're going to rush back here and look at our equation. Okay, we're not going to use this, and we're not going to use this equation. Okay, instead we will use this equation. So let's write down this equation. Natural log of A equals natural log of initial A minus KT. So no need to memorize this as long as you bring your rate sheet with you to the test. All right, initially, so by the way, this is initial, okay, initial. So a lot of people will mix up the numbers. So this is initially, and that's finally, okay. So finally and initially we're at 257 ppm. We don't put units inside the natural log, okay, that's just math rules. Okay, natural log of 257 initially. Finally is natural log of 15, so let me fill that in. Okay, minus the k. K, well, we already got k above, so 0.0575. I'm going to put that years in the denominator times t. And now all we have to do is solve for t. Okay, and solving for t will solve this problem. So do we know how to do our natural log math? Okay, really our calculator does it for us. So I'm going to take the natural log of 15 minus the natural log of 257 equals, okay, you see how I took this to the other side, equals, that minus sign still stays there, minus 0.0575. Okay, I can keep the units, or I'll add the units at the end of my problem. Divided by years, all of that times t. So I'll take this thing in the brackets and bring it down. This will isolate t. So I think I'm running out of time, so I will... okay, don't forget that minus sign also goes down with it. And actually the years flips back up to the numerator. So something like this on the exam. All right, so in the interest of time, I'll move on. We only have 20 minutes left. All right, let's move on to point number 7 here. So to get the final answer of the time for this to decay to 257 ppm to 15 ppm, you'll put this on your calculator. All right. We already talked about Le Chatelier's principle, but there is a multiple choice question on Le Chatelier's. Okay. So let's say we have a Le Chatelier's problem. What will the delta H be for this? Positive or negative? So notice here that I've written heat is a product side, so heat is also given off, just as product C and D is given off. So if heat is given off, that would be a negative value. Okay, negative value. This is also called an exothermic reaction. Okay, exo meaning outside, so outside of the reaction is given heat. Okay, so two things that we can do here. What happens if we raise the temperature of such a reaction? Okay, where will the reaction shift? Okay, raising the temperature meaning you're adding more heat. What will the reaction do to offset that? If we raise the temperature, it's going to shift left. Okay, you're adding heat by raising the temperature. The reaction will counterbalance that. We'll do the opposite, and it's going to shift left. Okay, there are other things we can do. There's a lot of other things we can do to mess with this equilibrium so that it's not at equilibrium. One thing we can do is we can remove maybe B. Let's try removing B. What happens if we remove B, reactant B? Okay, what will the reaction do as compensation? Where will it shift, right or left? You're removing B. You remove B, so what will the equilibrium do? It'll try to get back to its original composition, so what would it do? Shift left. Okay, it's going to make more B, right? Make more B. So this, in essence, is Le Chatelier's principle. Okay, be careful if you have gases, because they could, raise the pressure, decrease the volume. Then it's a little bit more tricky with gases. All right, part 8, bullet point 8 here. Remember, once again, let me give you a reaction here. 2 NH3 gas. Okay, equilibrium, because it's a back and forth arrow that I just drew, is in an equilibrium with N2 gas plus 3 H2 gas. Okay, so what would the equilibrium constant be? Okay. There's two ways to do it. You can do it this way with concentrations, because remember, these are gases. So gases can have a concentration in moles per liter. And what should I do with that H2? raise it to the third. Products over reactants. What should I do to that NH3 in my reactant side? Raise it to the 2. Okay, so that's one way to do it. There's also something called a KP. What we wrote previously was KC. Okay, just realize that you can also do a pressure here. So this would be a pressure N2 times a pressure of H2. We can cube it. All of that divided by the pressure of NH3. We have to square it. Okay, pressure. Okay, it can be in a pressure form or in a concentration form. Okay, so if you're going to calculate Kc for this reaction, okay, make sure that they are giving you equilibrium concentrations or equilibrium pressures. So make sure they are equilibrium. Okay, if they're not equilibrium, then you have to use Gator Rule. Okay, so look for the word equilibrium in the problem. Calculate Kc if the equilibrium concentrations are yada, yada, yada. Okay. Calculate Kp if the equilibrium pressures are blah, blah, blah. Okay. Equilibrium pressure, and it's an equilibrium concentration. Otherwise, you're going to have to compare it using the Q rule. Okay. So if you're plugging it in, make sure you're plugging in equilibrium pressures. The problem should tell you that. Or equilibrium pressures. The problem should tell you that. These are the equilibrium concentrations. These are the equilibrium pressures. All right, there's a question here on K, gymnastics. Okay, equilibrium constant in gymnastics. So let's say I have let's go back to our generic A plus B is in an equilibrium with C plus D. Okay, so this has an equilibrium constant K at some temperature T. Remember, we quoted at a specific temperature. Just realize the rules of the gymnastics here, flipping around an equation. What I can do is I could flip this equation. You see that I just flipped it here. And what will be my new equilibrium constant? It's not K. Okay, what will it be? Okay, when you flip a reaction, you take the reciprocal to get your new equilibrium constant. So reaction 1 is this. Reaction 2 has a new equilibrium constant, which is 1 over K. Reaction 2 has a new equilibrium constant, which is 1 over K. And there's another thing I can do. Let's say I can multiply all this out by a number, let's say 3. Okay, so 3C plus 3D is at an equilibrium with 3A plus 3B. Okay, what is my new equilibrium constant here? Okay, we multiplied it by 3. What happens to the equilibrium constant, the new equilibrium constant? It's not multiplied by 3, but it's raised to the power of 3. Okay? So we flip it, we take the reciprocal, we multiply it, we take it to the power. Okay? This is with the equilibrium constant, not with just the equilibrium constant. Realize it, just with the equilibrium constant. Flip it, you take the reciprocal, multiply by 2, multiply by 3, multiply by 4. You take it to the respective power. Okay? So 3, 3, 3, 3. The new equilibrium constant gets raised to the power of 3. Just be aware of your units of rate constant K. Okay, rate constant. Again, if you want to check this out, your sheet here. Make sure you are aware of any type of math involving units, but this is what you want to do for your rate constant. Units are going to change. And so multiple choice question on units. Okay, multiple choice question, units of K. All right. There's also a second order decay problem. Okay, so here K, rate constant, lowercase k, is decaying, and it's going to decay with second order kinetics. Okay, second order kinetics. So what would that be? What would second order kinetics be? Let's say A goes to B. Okay, what would be the rate law for this? If I tell you it's second order kinetics, okay, the rate law for this is, if it's second order, is going to be rate is equal to K times the concentration of A. What will be the power if it's second order? It's going to be 2. So for this specific equation, this would be the rate law, where the concentration of A decays by second order. Okay, so it's going to decay like this. Okay, and after some period of time, how much has it decayed? We will use this equation. Okay. Again, plugging it in and getting the answer out. Okay. Plug. Do you know this term plug and chug? Is that something you guys are aware of? Huh? Yes? Okay. So. All right, are there any questions so far? Now let's go over very quickly the written portion of your exam. So make sure you can access a copy and print it out, or use equation editor. So if it's easy for us to grade, it's also easy for us to give you points. So typical problem like this. So it says here, use an ice table to calculate the concentration of CO, Cl2, COCl2 at when initially you have 0.5 molar COCl2. By the way, I think I automatically see an error here, my arrows, so I'll probably change that. But this is at an equilibrium. And so we have to use an ice table for this problem. They tell you initially when you have 0.5 molar COCl2. Okay. So what will be the concentration of CO and what will be the concentration of Cl2? Right. So to construct your ice table, it's going to be like this. All right. They tell you let's read this out together. Calculate the concentration of CO, Cl2, and COCl2 when 0.5 molar of COCl2 decomposes. Okay, calculate the concentration of CO, Cl2, COCl2 when 0.50 molar COCl2 decomposes. So obviously you're going to have some of this and some of that when it decomposes. And because it's at an equilibrium, it's not going to decompose 100%. So here we're going to use the ice table. All right, so it's going to be, I've realized I've made a lot of errors here. I'm glad I'm going through this. 0.5, and that's 0, and that's 0. Okay, so it's going to go this way when you started out with 0.5 molar, so it's going to be minus x plus x plus x. Okay. So this will be 0.50 minus x will be plus x, and this will be plus x. Okay. So this is what you have to plug into k, but there is no k, so I will give you the k. I'll email you the k, or I'll give it to you out on Canvas. Okay. So I'll give you the k value. Check for your email, but what you want to do is plug it into this equilibrium constant k. All right, so k is equal to concentration of CO times concentration of Cl2 divided by COCl2. Okay, and this k is going to be, now we're going to plug in our equilibrium values. Okay, so x here, and x here is going to be x for CO, x for Cl2, that's going to be x times x, and COCl2 is going to be 0.50 minus x. Okay, so here you'll solve for x. All right. I'll give you more information on this problem. I think I made some mistakes here, so that's my fault. But then you're going to solve for x and then plug it back in. Okay. All right, let's hold off on that one, and I'll give you more information on that. So I'm glad nobody printed this out yet. All right, the last 4 or so minutes here. You have one of these problems. Okay, so we have a reaction. It has an activation energy of 100 kilojoules per mole. This is the rate constant. We quote the rate constant at a specific temperature. And what is the new rate constant at the new temperature? Right? So here we have K1, rate constant 1. We call that 0.286 liters over moles a second. Okay, and that is at a T1 of 500 K. We have a rate constant 2 that we do not know. That's what we're trying to solve, and that is at a T2 of 490 K. So we have everything we need to plug it in. I would convert this to joules per mole because R is in joules per mole. So I would convert this EA activation energy to joules per mole, and that just means multiplying it by 1,000. So 100 times 1,000 is 100,000 joules per mole. So now you're going to have to make sure you know how to use the calculator when you plug everything in and solve for K2. EA is 100,000 joules over mole. R is given to us as 8.314 joules per mole Kelvin. And that is 1 over T2, which is 490 K, minus 1 over T1, which is 1 over 500 K. Right, so that's the setup for one of the other problems here. By the way, the first problem I'll email you. I notice a lot of mistakes here, so just wait on word from me about that. All right, the final 2 minutes or so. We have a rate law problem here. Okay, so here we have a rate law. Here you're going to have to compare your experiments. Okay, so rate is equal to K. Okay, given the equation here, rate is equal to K times NO2. We're going to raise it to some exponent x times the concentration of CO times some exponent y. Okay, x can be 0, 1, or 2. Y can be 0, 1, or 2. And we also have to find k with the right units. Okay, proper units of k along with the correct value of k. All right. So first thing, we compare experiments. So I'm going to compare maybe I will compare 1 and 2. Okay, so that is rate 1 over rate 2 is equal to, rate law is K times NO2 raised to the power of X times CO raised to the power of Y. All of that divided by K times NO2 raised to the power of X times CO raised to the power of Y. Okay, so now you want to plug in your numbers here and also make sure you have the appropriate units. So it'll be 0.0050 mole over liter second divided by 0.080 mole over liter second. Moles over liters is big M. Okay, equals, and then you're going to put in, rate 1, experiment 1 concentration. Rate 1, experiment 1 concentration is 0.10 big M moles over liter. Rate 1, experiment 1 concentration is 0.10 moles over liter. Okay, rate 2, NO2, experiment 2 concentration, 0.4. Kind of like what we did in class. Okay, this is all raised to the X, that's raised to the Y. Raised to the X, that's raised to the Y. So from there you should be able to solve for X. You can compare another set of experiments to solve for Y, and that's how you will go ahead and proceed this problem. Make sure you write the final rate law with the right units and the right numbers for X and for the right numbers of Y. Right, and finally, a little bit overtime here, over a minute late. There's a problem where you have to use the Gator Rule. Okay, so these are gases. Okay, so here we have a Kc, which means we can express it as a concentration. Gases can be expressed as a pressure or a concentration. And we have to calculate Q and compare it to K. Okay, so remember, put Q first and then compare it to K and see which way the reaction will proceed. Remember what goes in here? Moles over liter. Okay, moles, not moles, but moles over liter goes in here. Goes into your equilibrium expression. It's not moles, but moles over liter that goes in. Okay, not moles, but moles over liter that goes into this expression. Right. So you're going to have Kc, and then you have Qc. If these are at equilibrium, Qc is equal to Kc. And if they're not equal, then you're going to use the Gator Rule to determine which way the reaction will proceed so that they will get to equilibrium. All right, so that is your exam, and I'll see you in the lab for those of you that are going to do the lab. And yeah, I'm going to email the class about problem 1. Seems like there's a lot of errors when I made the problem. All right, so hold off on that, but you can work on the other parts of the written exam. This is due Monday.